So now we're going to go over something called the remainder theorem. And this is a pretty amazing theorem from like 2,000 years ago that says something that I think a lot of us take for granted. I'll use an example here. Let's say you have a number 10 and you divide it by 3. And I want to know what the answer is. Well, you might recognize this form of writing it. I would say the answer is 3. And you got a little bit left over, right? You've got 3 plus a third. So we would say 3 is the answer, but it has a remainder, right? A remainder of 1. And if you remember the old days of long division in 4th grade or whenever you did it, this should seem a little familiar. Well, the fact is we can do all this stuff that I just showed you with 10 and 3 using polynomials. So I'm going to just put some vocabulary on this for a moment, and don't get too hung up on it, but this is how the vocabulary works. This is called the dividend, right? This thing up top. And the thing you're dividing it by is the divisor. And it produces something called a quotient and a remainder. So this is all the vocab you remember from 4th grade, right? I had to look it up first. So the interesting part about this is, let me just clear some room here. The only really important parts are the words quotient and remainder, because we will be asking you from time to time, what's the quotient, what's the remainder from a particular division? So it's good to know what we're talking about with those. So the interesting part about this is f can be any polynomial, and you're guaranteed that you can write the result, the quotient, as another polynomial with a remainder left over. So that's a pretty impressive statement. And another thing to notice about this is what does it mean if the remainder is 0? Like if the remainder is just 0, what does that mean? Well, it means that f just divided perfectly by x minus a. There was nothing left over. It's like if we divided 9 by 3. Okay, it would just be a nice whole number. Likewise, if you ever get a remainder of 0, what that means is you have found a factor of the polynomial. So it's very important when we find a remainder equal to 0. And let me just write that down. Another way of saying that is, here, let's say it like this. If x minus a is a factor of f of x, then f of a, okay, that's the remainder equals 0. And that is like the big important statement of this idea of the remainder theorem. So let's move beyond these abstract polynomials and try to do an example here using the remainder theorem to figure out whether something is a factor or not. So in this example, I'm going to say here, let's make this thing f of x equals I don't know, x to the 4th plus x cubed minus, I don't know, 19x squared plus 11x plus 30, okay? And I want to know, is x plus 1 a factor? Or in other words, the same question phrased differently is, what is remainder? What is the remainder of that big polynomial divided by x plus 1? So let's use the remainder theorem to figure it out. Remember what the remainder theorem said. Here's the remainder right here, f of a. So in this case, what's a? Well, if I say x minus a equals x plus 1, right? X minus a, see that over here? That's the x plus 1. So you can see that a has to be negative 1. So that means f of a, in other words, f of negative 1, is just you plugging negative 1 into all those terms up there. So I'll just do this kind of in my head a little quickly. Well, no, I'll write it down. Negative 1 to the 4th plus negative 1 cubed minus 19 times negative 1 squared. Can I fit it in? No, I'm running out of room. Plus 30. Okay. So what is that? Negative 1 to the 4th is 1 plus negative 1. Looks like we've got a minus 19 over here, minus 11, and plus 30. Okay, so keep working through it. 1 and negative 1 cancel out. Negative 19 and negative 11 makes negative 30 plus 30. Hey, look at that. Equals 0. So do you remember what that means? when f of a equals 0, that means x minus a is a factor. Or in other words, x plus 1 is a factor of that big polynomial, which I will not write again, of f of x.